Greetings and welcome to Disturbed. In the previous class, we discussed some basics about combustion, and we basically have to apply whatever material balance we've learned so far to combustion calculations, right? So we discussed about a fuel, then we discussed about combustion, about products of combustion, about complete and incomplete combustion. Then we discussed about the calorific value of fuel, which is basically of two types, either gross calorific value or net calorific value, depending on whatever state we get water in. So if water is in liquid state, then it's the gross calorific value. And if it's water in the vapor state, then it's the net calorific value. All right. And after that, we discussed about flue gases and stark gases, where we discussed that flue gases are the products of combustion. Dry flue gases are basically products of combustion without considering water. And wet flue gases or stack gases are gases with water, all the products of combustion, including water, right? Then I also gave you some basic information about air, percentage excess, how to calculate oxygen supplied from air, and how to calculate nitrogen supplied from oxygen supplied and oxygen supplied from nitrogen supplied, right? So we discussed all these things. So you could just go back to the previous video, whatever we have discussed about combustion, you can just go through before you start with this particular video. So in today's video, we'll be doing numericals based on material balance, which is related to combustion. All right, so we're going to do that. So make sure all the concepts that have been taught in material balance, whether it is making a block diagram, whether it is material balance without chemical reactions or material balance with chemical reactions, especially material balance with chemical reactions, you need to be very clear about all that. So finally, you can apply all your knowledge in material balance over here in combustion. All right, combustion is a very difficult, I'd not say difficult, it's rather confusing. So make sure that all your conceptual knowledge, whatever you've learned so far, it's all clear. It's there in your head, crystal clear. All right. So make sure that before you start with this video, you go through all the videos that have been taught before, and just if you have some doubt somewhere, then please just for once go through that video once again. All right, material balance with chemical reactions, I've explained quite much in detail. Everything I've explained, we've done many problems in that video. So you could just refer to those videos and do those problems, solve those problems, try to solve those problems yourself. If you still feel uncomfortable, you can refer to some other books on chemical process calculations, and you can just go through certain example problems or unsolved problems of those books so that you have that confidence while you're solving combustion problems. All right, so we'll go for combustion problems now. So make sure that you're understanding with clarity. All right, so we move on to the first example for combustion. Coke. Now coke is a solid fuel. All right, coke is a solid fuel. So coke containing 85% carbon and 15% ash is burnt in a combustion chamber such that 90% of the carbon present in the coke is burnt. 95% of carbon forms CO2 and the rest of it forms CO. Air supplied is in 40% excess. Find composition of flue gases in mole percent, given that all percentages are by weight. So let's solve this problem using whatever knowledge we have for material balance. All right. So we'll go ahead and form the block diagram for this problem. So we basically have our combustion chamber, right? So this is my combustion chamber. Then after that, we have coke containing 85% carbon and 15% ash, right? and these percentages are by weight. So the basis that you're going to take for this particular problem, it is going to be, since it's percentage by weight, therefore it's going to be 100 kg coke. All right, so it's 100 kg coke. So when you put that in, so it is basically 85 kg carbon and 15 kg ash, right? That's what is going in. And then you have the products of combustion. Water is not included in the products because there is no hydrogen over here. And then of course you'll supply air. So I'll just put air over here. So air is supplied as well. And air is 40% excess. All right. So everything is again by weight. So therefore I'm going to say that we have 23% oxygen and 77% nitrogen, right? That's there about air. All right. And then finally, in the products of combustion, that is the flue gas, basically, we get carbon dioxide, we get carbon monoxide, which is also there because they have mentioned that some of it is there to form CO. Then we have unreacted oxygen, we have nitrogen. All right, these come under your flue gas. And apart from that, whatever ash or unreacted carbon that is left, that all we are not considering in flue gases, so we are not bothered about that. All right, so just make your problem as easy as possible. Don't unnecessarily complicate by including everything. That okay, I'll include everything, I'll include whatever carbon has not reacted. That's not required. That's not required. We don't have to do a proper mass balance over here. So we are not going to include that 15 kg ash and the carbon that has not reacted. We'll come to that. All right. So then once we are done with this thing, after that, we'll move on and work on the stoichiometry. So the stoichiometry states that carbon, it can react with oxygen to form carbon dioxide, which is one thing. And then you have carbon, which can also react with oxygen to give carbon monoxide. Correct. Both these reactions are going to take place because carbon dioxide and carbon monoxide, both of them are being produced. All right. Now, another thing that they are saying is 90% of the carbon burnt, 90% of the carbon present in the coke is burnt. So, carbon burnt is equal to 85 kg, that is the carbon present, into 0.9, that is 90% of it. So this is going to be 85 into 0.9, so that is 76.5 kg, right? 76.5 kg. This is the amount of carbon that has burnt. All right, this is the amount of carbon that has burnt. So again, we have to use it in stoichiometry. So it would be better if we convert everything into moles. But let's go for the mass. All right, let's go for the mass basis. So again, 95% of carbon forms CO2. So carbon forming CO2 is equal to 76.5 into 95%, right? So 0.95. Remember, all the percentages are by weight. So you need to keep everything in weight before you start actually conversions. All right, so 76.5 into 0.95, that is 72.675 kg is the carbon that is forming carbon dioxide. And then carbon forming carbon monoxide is the remaining. So it's 76.5 into 5%, right? So that is equal to 3.825 kg. Or you could also simply subtract 72.675 from 76.5. So that would have also given you this value, right? It's both ways, that's correct. All right, so this is the carbon 72.675 that is being used over there in forming carbon dioxide. So in the first reaction, that is carbon dioxide reaction, we are going to have 72.675 kg of carbon. And in the second reaction, we are going to have 3.825 kg of carbon, right, for forming carbon monoxide. All right. So now, now when we are using all these concepts in stoichiometry, so we have to make sure that we get the moles. So we are going to divide it by 12. So whatever we have over here, by stoichiometry, we can say that even oxygen, all right, let's not go there. Okay, so we have these many things. Okay, we have 72.675 by 12 kilomoles of carbon that are there to form carbon dioxide, and we have 3.85 by 12 kilomoles of carbon that are forming carbon monoxide. All right, so that's what we have with us for now. Great. Now let's just play with the stoichiometry for some time, or should we go with mass balance? We can go either way. So I'll go with the stoichiometry. So from the stoichiometry, we get that from the first reaction. If we consider the first reaction, stoichiometry of the first reaction, and over here we see that the ratio is 1:1:1. So it's going to be 72.675 by 12 kilomoles of carbon are going to react with 72.675 by 12 kilomoles of oxygen to form 72.675 by 12 kilomoles of carbon dioxide. That's going to be true. All right. And over here, it's 1:0.5:1, right? So 3.825 by 12 kilomoles of carbon are going to form 3.825 by 12 kilomoles of carbon monoxide, right? And half of the carbon that is reacting would be oxygen over here. So that's going to be 3.825 by 12 into 1 by 2, right? This is what we have so far. All right. This is what we have from the stoichiometry. All right. So we'll keep this into picture. Okay. We'll keep this with us. And then we'll go further towards the question. So again, in the question, they are saying that 95% of carbon forms CO2 and the rest of it forms CO. So that we have taken into account. All right. Now, air is supplied in 40% excess. Now remember, whenever we need to calculate percentage excess, all right, in the formula for percentage excess, we have B supplied minus B theoretical upon B theoretical, right? That's what we have. So we need both theoretical demand and supply. All right. All right. So basically we need theoretical demand. We have percentage excess. So from there we'll get B supply. So we simply need theoretical demand. So how do we get theoretical demand? So for getting a theoretical demand, we need to keep in mind that what is the desired reaction? All right. What is the desired reaction? What do we want that should definitely happen? So basically what we want is that all the carbon over here should get burnt to form carbon dioxide. That is the desired reaction, right? Now, some of the carbon is burning to form oxygen, some of the carbon is not burning. That's different thing. But what we want is that the combustion should be 100% complete. That is the desired reaction. So always remember, whenever you are doing combustion problems, specifically combustion related problem, you must know the desired reaction, because there are so many reactions that most of the students, they get confused that what is the desired reaction? There is only one desired reaction. There are no 2, 3 desired reactions. There is only one desired reaction in most cases. All right. However, if let's say you have different components, let's say you have carbon here, sulfur here, in that case, you'll have more than one desired reaction. But again, for each component, let's say you have carbon, then for carbon, you'll have only one desired reaction. Similarly, for hydrogen, you'll have only one desired reaction. There would not be more than one desired reactions for a single component, right? So for carbon, the desired reaction is going to be that we want all the carbon to form carbon dioxide. This is what we get. This is what we want. So from the desired reaction, why is desired reaction important? Desired reaction is important because from here, we are going to get the theoretical oxygen demand. All right. From the desired reaction, we'll get the theoretical oxygen. So what is the desired reaction? In the desired reaction, we want that all the carbon, that's 85 kg of carbon, should burn to form carbon dioxide. That means 85 by 12 kilomoles of carbon should react. Right. So what is the theoretical oxygen demand for 85 by 12 kilomoles of oxygen? 85 by 12 kilomoles of carbon. Obviously, from stoichiometry, you get the same number of moles are required. So theoretical oxygen demand for this is going to be 85 by 12 kilomoles. That is 7.08 kilomoles. This is going to be the theoretical demand. All right. Then they have given us percentage excess as 40%. So as I told you, if it's 40%, then the oxygen supplied is going to be theoretical, oxygen theoretical into 1 plus 40 by 100, that is 1.4, right? So this is going to be oxygen theoretical, that is 7.08 into 1.4, that is 9.9167 kilo. All right, approximately, this is what we are going to get, 9.9167 kilograms. All right, so this is what we'll get oxygen supplied. So over here, we have oxygen supplied as 9.9167 kilo. Remember, as you are going ahead with your calculations, you need to complete this block diagram. And once your block diagram is complete, half or most of your problem is solved. Then you only need to see what they have asked in the question and go ahead. All right. So then once we are done with this, then we'll go on to nitrogen. So nitrogen supplied, as I told you, how do we relate nitrogen and oxygen? So nitrogen supplied is basically oxygen supplied into. Now remember, it's always the percentage of this gas, whatever is in the LHS. So percentage of nitrogen upon percentage of the gas which is being multiplied. So oxygen. Remember that. And since oxygen supplied we have calculated in kilomoles, right? Since this we have calculated in kilomoles, so this is going to be in mole percent. Remember that. This is going to be the mole percent. All right. So this is going to be oxygen supplied is how much? 9.9167. So 9.9167. What is the mole percent of nitrogen in air? It's 79%. Upon what is the mole percent of oxygen in air? It's 21%. So nitrogen supplied is basically this. So when we do our calculations, we'll get 37.305 kilomole. All right. When we do the calculations, we'll get 37.305 kilomoles. That is nitrogen supplied. All right. So we have over here 37.305. All right. Now, as I told you, nitrogen never ever reacts in combustion. So nitrogen, whatever we have supplied here, same is going to come here. So it is going to be 37.305 kilo. All right. So you don't need to worry about that. It's always going to be the same 37.305. All right. So when we have this thing, then in that case, we'll move on further. All right. So oxygen supplied. Next, we have to calculate what is the carbon dioxide here and carbon monoxide here. So that as we discussed, that these many kilomoles are going to be here. So from the stoichiometry itself, we've got 72.675 by 12 kilomoles of carbon are forming carbon dioxide. So that is going to be, by stoichiometry, we get that only these many moles of carbon dioxide are going to be produced. So that is 72.675 by 12, that is 6.056. All right, so that is the carbon dioxide that has been produced, 6.056 kilomole. All right, and then carbon monoxide produced is 3.825 by 12 from the stoichiometry. Hopefully this part would have been clear. So it's going to be 3.825 upon 12. That is equal to 0.319. All right. So it's 0.319 kilomole, right? All right. Then we need to go ahead and get this oxygen. So for oxygen, what we are going to do, we are going to use the oxygen balance equation. Oxygen balance. All right. So what is oxygen balance? Oxygen is in the reactants. Remember, oxygen is in both cases, it's in the reactants. So oxygen is going to be consumed, right? Oxygen is going to be consumed. So we'll get oxygen in minus oxygen out is equal to oxygen consumed, right? So oxygen in, you have already written in the block diagram, it's 9.9167, right? Then oxygen consumed, this is what we need to calculate. So again, this information we get from our stoichiometry. So oxygen consumed is basically oxygen consumed in the first reaction, that is 72.675 by 12 kilomoles. So that is equal to 6.056. Plus oxygen consumed in the second reaction, that is 3.825 by 12 into 1 by 2. So that is 0.319 by 2, which is equal to approximately, we can say 0.16 kilomoles, right? So it's 0.16 kilomoles. All right. So the total oxygen that has been consumed is 6.216 kilomoles. All right. So then we have in the oxygen balance equation, we have oxygen in, we have oxygen consumed. So oxygen out. Just a minute. Yeah. So oxygen out we can get as, from the balance equation itself, we are going to get oxygen out. Oxygen out is equal to oxygen in minus oxygen consumed, right? So oxygen in is nothing but whatever has been supplied, that is 9.9167 kilomoles, minus whatever it has been consumed is 6.216 kilomoles, right? So this altogether is going to be 3.7007 kilo. All right. So this is oxygen out. So then we have oxygen out over here in the block diagram. We write it as 3.7007. Now just look at the block diagram and analyze whether everything that is required in the block diagram, is it complete or is it incomplete? So from the block diagram, we can see that we have inlet, whatever has been fed. We have outlet flue gases, whatever have been fed. We have air, whatever has been fed. So we have everything in this block diagram. So our block diagram is complete. Our block diagram is complete. Once our block diagram is complete, majority of our work is done. Right, majority of our work is done. All right, now we simply have to go and play with the question, whatever they are asking. For example, in this question, they are asking you to get the composition of the flue gases in mole percent. So we have the flue gases, we have the total moles of the flue gases. Now what we only have to do is we have to convert them into its composition, that is mole percent. So let's go ahead and do our conversions. So we have component, we have their moles, and then of course their mole percent, right? So each component, I'll just list it out: carbon dioxide, carbon monoxide, oxygen, and nitrogen. So the moles of carbon dioxide are 6.056 kilomoles, right? 6.056 kilomoles. In carbon monoxide, it's 0.319 kilomole. Then oxygen, it was 3.7007. Yeah, 3.7007 kilomole. And nitrogen was 37.305. So it's 37.305 kilomole. So when we add all of them, we get the total number of moles as 47.3807. These are the total number of moles. So now, if suppose in the question they would have asked you to find the volume of this gas, the flue gas, you have, if suppose they would have told you that the flue gas is coming at a pressure of let's say 200 kilopascal and at a temperature of 573 Kelvin, then find the volume of the flue gas. So you have number of moles of flue gas, so you would have simply put it as V is equal to nRT by P. All right, so here N would have been 47.3807. So that I'm just giving you this information so that if you get questions, you know how to play with those questions. All right, whatever we need to do is simply complete the block diagram. Once our block diagram is complete, we don't have to work more. We only have to manipulate whatever we have found in the block diagram. All right, so over here, they've simply asked us the mole percent. So we are just going to divide the individual moles by total moles and then multiply it by 100, right? So the mole percent is going to be for carbon dioxide, it's going to be 12.782%. Then for carbon monoxide, it's going to be 0.673%. For oxygen, it's going to be 7.811. And nitrogen, since it consumes maximum, therefore it's going to be 78.734. So if you add them, they should come out to 100. So 325, 510. Yeah, it comes out to 100. All right, so that's your result. All right, that's your result. That's the answer. That's what the question was demanding. So make sure what you need to do while you're dealing with a combustion problem, you only need to, not just a combustion problem, any problem related to material balance or any problem related to material balance of chemical reactions, you only need to complete the block diagram. Once your block diagram is complete, then there is nothing more you need to do. You just need to manipulate those values again and again. All right, so make sure even if the question comes in gate or in any form, you just complete the block diagram. Once your block diagram is complete, all the other problems are going to finish. All right.